plan for this lecture, it's going to be pretty short, like less than an hour, hopefully. So we'll have early lunch. So the plan is to see two simple reductions that show APSP hardness of some graph problems. And most of the work was done by Nick, really. Like he showed how you go from APSP, which is like a hard problem, computing all distances in a graph, which is like a complicated problem to reduce from. He showed us how to reduce to negative triangle, which is like a very simple problem, very local. You don't have to compute all these long paths from everywhere in the graph. You just have to find like a very small structure in the graph, just this negative triangle. And then that's really cool, and that's what gives, like in my slides, I have a bunch of APSP hard problems, and by now we have like, I don't know, 20, 30 APSP hardness results. All of them go through negative triangle, and then you reduce to the other problems. So I'm not going to show you 20 or 30. I'm just going to show you two. Pretty simple, but they kind of look a bit different from each other. And then you can build on them to get more reductions. They somehow explain some of the high-level structure of reductions. And actually, in the exercises, you will build on them. So that's like the first part of the talk. And then in the second part, I'm going to talk about negative triangle versus zero triangle. So negative triangle, right, is what we were talking about. You want to find a triangle with where the sum of the three edge weights is negative. And zero, you want the sum to be equal to zero. And so you can start thinking about, if you get bored with the reductions, you can think about what you think about this. Like, which is easier of these two problems? Which is easier, which is harder? Finding a negative something, triangle, or this is going to be a general reduction we will show. Like finding whether there exists something that's negative, that's like smaller than something, or whether finding something that has weight exactly something. So which of these two things is easier? So we'll show, a reduction in one direction. And just to summarize what happened yesterday and today, right? So yesterday we had threesome, and we showed a bunch of equivalent variants. And then we also saw a bunch of geometric problems that are hard on the threesome. And one of the equivalent variants was this convolution threesome, in which you had to work hard with hashing and stuff to get to the equivalence. And then on the exercise sheet, there was a question reducing from convolution threesome to zero triangle. This was like a 2-3 reduction, kind of. It's a zero triangle. It's like, it's kind of like negative triangle. It's like an n-cubed problem. You have to try all triples. And if you could do subcubic, then you get subquadratic for convolution threesome, which refutes the threesome conjecture. So it's a hard problem, just like negative triangle is cubic hard. But from here, it's from a different conjecture. Here it's from APSP. And this reduction, I guess not all of you have done it probably in the exercise. This is, like, I'm not going to, there were some hints and so on. If you're interested, you could look at the exercise sheet to see how it works. But basically, I can say that it's like, this is a problem in which you get an array. And here it's like a matrix kind of thing, like a graph. And so it's just a question of how you arrange the numbers from the array to a graph or to a matrix. It's going to be smaller, like a smaller matrix than the thing. And so that triangles correspond to like this convolution thing, aj and k such that k equals I plus j. So it's not like a very deep, I would say, reduction. It's just like rearranging the numbers in certain ways to get it. So yeah, I'm not going to talk about this, but So this is just giving you extra motivation for what I asked you a minute ago. Like, what is the relationship between zero triangle and negative triangle? It's like two problems, one from each class. And so we will see. OK. And then here, right, we have APSP, which is like our hard problem, our famous problem. And it reduces to this matrix multiplication, min plus matrix multiplication. And then that reduces to negative triangle with this kind of magical reduction that we just saw. And so now let's just have fun, Let's just take negative triangle and then reduce to some problems. So I'm going to write one problem, and you can tell me how to do the reduction. So the problem is n pair shortest path. So we're given a graph. It has weights. The weights are some integers. Let's say they're positive. So we're given a graph, and its weight. Let's say it's undirected. Just to be simple. And you're also given a set of pairs. Of size n. So you get n pairs of nodes, and you have to return the distance for all these pairs. Okay, so we have a graph, and you don't want to compute all pairs shortest path. You only want to compute n pairs, but you're given which n. Like you're given, this is S1 T1, and this is S2 T2, and so on. And you want to know, what's the shortest path? What's, separately for each pair, what is the shortest path? And it's important that we are given which pairs. Like if I asked you give me some n distances in a graph, that's kind of easy. Anyone see why how can you in linear time or like n squared time find some n distances? Dijkstra, exactly. If you run Dijkstra from a single source, you get this shortest path tree that tells you the distance to everybody from that source, and that's n pairs. But that it's not like I give you these n pairs. They don't look like a single source and all targets. They look arbitrary. We will show that it's an n cubed problem, not n squared, but n cubed. And it's kind of weird. Maybe like Nick worked so hard to go from a shortest path problem to a triangle problem, and now I'm trying to go the other direction. But the point is now it's like a much seemingly much easier problem. I just have to compute n pairs, not n squared. And so like the statement that I'm proving here, that we're proving, is that it's equivalent. N pairs and all pairs is equivalent. It's kind of bizarre, right? It's not what you'd expect. And the only way we know how to prove it is by going through negative triangle. Like I don't know how you would prove it like directly. Okay. So let's prove it. So write the n pair. And there's an easy direction here. Typically for these graph problems, this direction is easy. Like APSP is like the hard shortest path problem. It kind of solves everything for us almost. So this direction is easy. Like if I give you all pair shortest paths, you can find the n pairs like that you care about. It's just subset. So let's talk about the other direction, and it's a reduction from negative triangle. So here's negative triangle. I'm gonna remind you of the problem. Right, so you have so it's the graph is tripartite like this. So let me draw it bigger. Has parts x, y, z. And yeah, the question is, are there three nodes such that the sum of these three edge weights is negative? Okay, so how do you go from this problem to n pair? I'll give you a minute. So the weights are just integers, like from minus u to plus u. It doesn't matter, it's just some polynomial. Okay, so how would you go from like a triangle problem to a shortest path problem? Yeah.
You can add one more layer to the right side and add the Z to X just in that layer and then just check like source to sink
Uh-huh.
like N of P.
Yeah. So the idea is really to go from triangle to path, and I think what you're saying is so it's like, you know, we look at a node. A triangle is like a path from the node to itself, really. Right? It's like, and like the shortest, the minimum triangle or negative, like negative is kind of like minimum. Like if you find the minimum, it's like you also know if it's negative or not. So it's like you're trying to find a cheap path from a node to itself. But just asking for the, give me, Si and Ti, saying they are like the same node. That's kind of like doesn't. I mean, the distance from node to itself is 0. It's not like whatever. So so we have to do what he said. So try to somehow make like maybe another copy and then force the path to like make another layer. So like. So we take the graph and we somehow open it up. X, Y, and Z are the same, but then we look here and we put another copy of X. It's like these edges, they go here. These edges, they go here. And then these edges, they don't go back. Instead, they go here to this new copy. So it's really just, X prime is just a copy of X. So like just like X prime is just X prime for every X in X. So I'm not going to be very formal because it's pretty simple, but basically, if there's some node X here, then it appears here, but it also appears here. And then the edge weights that we put here could be like just the same, really. Like if you have a node Y and you have some weight WXY, then from the X to Y here, it's WXY. It matters, yeah. Okay, so let's talk about that. So here we have negative weights, and I'm defining a shortest path problem, so I don't want negative weights. They make a mess in shortest path problem. So how do we go to get positive weights? Yeah, we just add stuff. So let me use a color. So I just add, something large like. So putting just plus u will make it positive. Everything is at least minus u. But just u is a little bit risky. Does anyone see like a potential issue with this reduction? Directed versus undirected, yeah. Yeah, so, right, it's like, I want the path to go forward, like to go from X to its copy. Okay, so what's the idea here, right? We want to say that I'm going to give n pairs. For every X, I'm going to give a pair that's X and X prime. So there's n pairs. And I want to say that I look at the distance for that pair, and that is going to tell me if X is in a negative triangle. And so like I'm imagining that paths, they go like this. You start at X, you go to some Y, some Z, and then to X prime. But what if it zigzags? Instead of going like this, it goes from X to Y to some other X, and then to some other Y, and so on. Here, it would correspond to taking like a longer cycle. Like, I don't know, you do like this, right? And maybe that's cheaper. Sorry?
Can you add an offset to all the edges going back?
So it's I'm trying to define an undirected problem. So I don't know which edge is going back or forward.
If you add like the U to be big enough, then
Yeah.
You're going back and forth.
Exactly. So if I put like 4u, then that makes it not a good idea to zigzag. Because like, okay, let's say like going straight, it's just 3 edges. So the distance will be like 12u. So the claim is like x is in triangle, a negative triangle, if and only if the distance in the new graph, let's call this graph H and this is G, between x and its copy is less than 12u. Okay, so like the good case is you take like 3 edges, you go from x to x prime, and then you're also choosing a path that corresponds to a negative triangle. So the weight is like 12u from the orange contributions, and then from the 3 edge weights, you get something negative. So you get less than 12u. And now if you cheat, if you go like this, then you're getting 5 edges. And then that's like 20u. And that's just, there's no way it's going to be worth it because like the original edges, they're like at best like a minus u giving you each time. So okay, fine, like 5 times 3, like for every plus 4, you get a minus u or something. But that's already like 3u, so that's 3 times 3 times 5, that's 15. So it's not worth it. So this adding like a large weight is like going from directed to undirected, really. It's like forcing the shortest path problem to go along the layers. Does it make sense? Okay, so that's the first simple reduction. So the second problem is second shortest path. I lost the good chalk. Oh, here. So again, we're given a graph. It has weights. This time it's going to be directed. It's going to matter. And we're also given a pair, S and T, and the shortest path. And the goal is to return like a second best shortest path. So a shortest path that's the best that is not equal to the one I gave you. So you get a graph and a path. Some shortest path, and then you have to find a different one. So you have to find a path that's, maybe like this. It has to differ in one edge. So how do we get the reduction?
If you want to reduce from this to APSP,
Uh-huh.
you could, for all the edges in this path, add like a really large number. A really large negative
Yeah.
number, sorry.
Yeah.
Subtract
Yeah. So it's actually a case where going in this direction is not trivial. So reducing this to APSP is not trivial, and it really works the way you're describing. You compute APSP. You also compute APSP on the graph where you make the edges on the path longer, and then you try to combine the answers. Like for every node on the path, you check what's the distance if I in the original graph, but then like from here to there, like, I have to take a different. It's actually one of the bonus exercises, so you can try to figure it out. But let's do the hardness direction, like showing that this problem is not easier. It's not subcubic, and it's actually interesting. Like this problem. So if it was undirected graph, then this strategy I was just describing now could actually be made to run in linear time, in squared time. So this problem was known to be quadratic time for a while, and I think people thought that the directed case would also be easier. But then this hardness result came and showed that it's very hard. Let's do it here. So again, we're reducing from negative triangle. It's just going to look a little bit different. Any guesses? And then what?
Then the second shortest path would correspond to some negative side.
Yeah, it's along these lines.
But I think again you need to make a copy or something on the side.
Yeah, so let's try this. So you're suggesting something like, I'm gonna put like a cheap path. From S to T. So there's S and T. This is a cheap path, let's say epsilon weights. But then but I need to, it's directed also. Okay, but what is the second shortest path? So I have to, go out of the path. Then when I go out, it should correspond to the minimum triangle. So that's exactly the idea. So let's call these nodes like x1, x2, x3, like xi, up to xn. So these would correspond to these nodes. So this is like going to encode x. And then when you are here and then you exit, it should be like you're going to y. So let's make a copy of y, a copy of z. Like I want you to exit here, take some edge like this, and then come back. So like this, the second shortest path will have this form. It will leave the path at some point, go and come back right then, and then continue to t. And like the cheapest way to do it would correspond to the cheapest triangle in the graph.
So you will make two copies here of x, xi followed by xi.
Yeah, you could think of this as like two copies of x, but you could it's fine even just like to the next one. It will just go back to the next one.
You again need to ensure it only takes 3.
Yeah, like I think okay. So now we have to choose the weights carefully, so that it's not a good idea for you, let's say, to exit and then come back later, because so it's directed. So that's taking care of itself. It's directed. And undirected, the problem is easy, so it's not going to work. So okay. So how it's going to work? It's again you put the weight of the like xi. So you use the original weights. But then you add something kind of clever. Sorry?
Can you write bigger?
Yeah. Okay, so I added these orange weights that will do what I described. And the idea is, let's say you decide to exit here, like to delete this edge, like not take this edge. Then the best way for you would be to go as far as possible and then exit. And the reason is, like, the further you go, this contribution gets cheaper. So the orange thing is like really big. It's like times u, or maybe you can put u squared just to be completely sure that like the orange is like the most significant contribution to the weight. So you should really care about optimizing the orange and then care about optimizing the original weights. So okay, so one edge has to be different. Let's say it's this edge. Then the best strategy is to go as far as possible and then exit the path, because then you get the least amount here. Okay, so you exit, you take some edge, and then you have to come back. And then this means that the earlier you come back, the cheapest it would be, because now it's not minus I, it's plus I. So then you have to come back as early as possible.
Why can't you come back like even earlier in the lecture?
So coming back earlier and then going like this?
It would be a path.
Is that a piece of
It has to be a simple path. Yeah. It has to be a simple path.
And what goes wrong for underwriting?
For undirected,
You could take like path from y to x. You could just
But why can't you fix that by adding
sorry?
Can't you fix zigzags by adding like scale everything else by
I mean, look, the directions here are somehow playing a role. It's like you look at the node, this node has an edge coming from here, but you can't really take it because of the directions. So it's like you could have just gone like this if so like having like this asymmetry will not be possible without the directions. So if I didn't put them, then there would have been like one clear good choice, like either going early or like this. So anyway, I'll leave it at that. It's in the exercise sheet, like the same problem. So you can like convince yourself of it, that the correctness. Okay, good. So negative versus 0. Oh, by the way, this problem, so in the exercise, like the second exercise, is about a problem called radius, which is finding like a node that's closest to everybody in the graph. So it's again one of these shortest path problems that looks easy because the answer is just one number. And the question is to prove that it's equivalent to APSP. So it's like, and here's a hint, like without the hint it may be difficult. So the reduction from negative triangle to radius looks like this. So I would start by, look at this reduction and then try to go to radius. Try to encode this problem this construction with all the n pairs. Like there are these n pairs, and you're trying to find the one where to its partner it's as close as possible. Try to encode that with the radius. This is like a hint.
Can you please provide us until the end of this workshop with the three chart shows the relation between different problems and which one can be reduced to sum the other one?
Sure, but like so far everything is equivalent. So like let's say the APSP stuff is all equivalent. Yeah. And then for the other stuff, so now this is what we're doing.
I think you just missed it, but what was the reduction from second to first half to APSP? Just about a re-rating of the...
So that I didn't tell you in detail, but yeah, the idea is you compute APSP and then you reweight the weights, or you delete the edges of the shortest path that you're given, and you compute APSP, so you get these two distance matrices, and then you try to combine them together in a certain way in quadratic time to get the answer. So let's try to do it here, maybe. Okay, so now we're doing a reduction from, okay, I guess you have a guess, negative or zero, which is easier, which is harder. So we're going to show an arrow now between this and this.
Would zero be harder? Because I feel like... Oh, no. Oh, shoot. I was thinking when you have zero, you could subtract some values from all of the weights and then find a negative triangle would... Oh, it doesn't necessarily imply one or the other, sorry.
Yeah.
Maybe you can use a solver for negative triangle to solve zero triangle. So you first apply the negative triangle to identify negative triangle, and then you flip on you take the minus of all of the weights, and then find negative triangles. If those overlap.
The problem is it wouldn't be the same triangle.
Yeah, so you probably have to identify negative triangles.
Yeah, so you don't think it's going to work. I think what suggestion is like, if something is negative and then I flip and that same thing is somehow suddenly positive or not, then it would have been zero. Kind of. I think that's the idea. And that doesn't work because you just call it once, you get yes. You don't know which, or you get one triangle, fine. You negate, but then you don't. Maybe a different triangle is now the positive one. That doesn't quite work.
I guess maybe that the zero triangle is harder because the negative triangle is like finding, as you were saying, it's kind of like finding the minimum weight triangle, whereas a zero triangle may not be the minimum one in the instance. So that's the instance.
Yeah, that's correct. I mean, my intuition would have been similar to like the previous answers that a negative should be harder, but actually it turns out that this is correct. So this is what we can show. I mean, with the other direction could be correct, we just don't know. And in fact, showing the other direction would be amazing. Do you see why? Yeah, it would collapse something. Like it would mean that three-sum reduces to APSP, which we don't know. So what we have is this problem, the zero triangle, which is kind of cool because it's harder than two conjectures. So it's like a super hard problem. If you break it, if you solve it faster, you break two conjectures.
Is there any barriers to showing this? Like if three-sum can be reduced to APSP, is fair enough? The direction
No, I don't think so. Yeah.
You might have the same lower bound under both conjectures.
It's the same. It's n cubed lower bound. Yeah.
And just to be clear, zero triangle is equivalent to threesome, right? If the arrow goes to
No. So this it's not.
it's not.
It's not. Yes. It's from convolution to zero. It's just in one direction. And in fact, yes, if you could prove an equivalence, then you would get. It's also amazing, because then APSP reduces to a threesome. Okay, so hopefully that's enough motivation for you to care. So let's talk about this negative to zero. And in fact, I'm going to do positive, not negative. It's the same. You just negate everything. Just easier to think about positive. Okay. So I did and then the reduction here is going to be like a general thing. I'm not really going to talk about triangles. Like it will be specific to triangles, but like you should think of it as reducing like this kind of question to this kind of question. It will apply for many other problems. So how do you do that? So I think like a first idea is to say, well, if I want to know if something is positive, so I ask, is it equal to 1? If it's 1, great, it's positive. If not, I ask 2, is it equal to 2? And then I try 1, 2, 3, 4, 5, everything. It's too many things, too many questions. But then, okay, once I ask like up to 100, then if it's not and it's positive, then it's like larger than 100. So then it's like if I solve it approximately, kind of, then maybe I can figure it out. So for some of you who do approximation algorithms, for example, this is kind of what's happening here, but like it will not look like this. But it's like, first you realize, oh, it's far from 0, and then you do some kind of bit scaling, like some approximation to reduce like the optimization to the exact, to approximately exact. So that was one intuition. Now let's look at another intuition with bit representation. So I wanted to ask, is x greater than t? So I have some target, and I want to know if some value is greater than the target. So I can look at the bit representations. Okay, so if you look at the bit representation, you start from the most significant bit. Okay, if there's 0, well, then is probably also 0. If it was like 0, 1, then t is greater. But okay, they could be the same. And if it's 1, well, it could be 0 or it could be 1. But at some point, you will see a gap. So you will see, if x is indeed greater, then if you look at a certain prefix of the bits, you will see, for the first time, you will see a 1 here and a 0 here. So what it means is that, and then when that happens, then the difference between them is exactly 1. So you will get that this equals this plus 1 for those prefix of bits. So formally, here's a lemma. If x is greater than t, then there's some I such that x over 2 to the I is equal to t over plus 1. So x over 2 to the I floor, this is like looking at the first I bits of the bit representation. And then you look at the first I bits, and you see that they're equal to exactly this plus 1. So if it's greater, then there must be an I for which this happens. Actually, it's if and only if. Okay. So how do you use this for reduction? So the idea is really, you look at all your numbers, you only look at the most significant bits, and then you call the algorithm for exact only on those bits. Like you delete all the other bits, and you ask, is it equal to 1? Is the answer equal to 1? If you found it, then you're happy. It's not quite going to work, but let me write it anyway, and then we will fix it. Okay, so here's a reduction. It's, think about what's wrong with the reduction. This is from positive triangle to zero triangle. So when I say 0, I can say 1. Like, is the triangle equal to 1, not necessarily 0. It's the same thing, right? You just add like a 1 to some of the edges. Okay, so for I log u. Okay, so this is exactly what I said. You go over the bits, like I from 1 to log u. You look at the first I bits. So you define the weights to be the original weights divided by 2 to the I floor. And then you make a call to the 0 triangle problem or the 1 triangle problem with the same graph, but where the weights got truncated. If you got a yes, you found a triangle of weight 1, then you're happy. You say yes, I know that there's a positive triangle in the graph. If it never worked, then you say no.
There might be some carries from the lower significant bits.
Yeah.
Which affect the higher significant bits.
Yeah. Yeah, so that's really the problem. The problem is that there isn't like a one number, like we're talking about. Like this lemma is correct, but if it's about just one number. But what we have, in fact, is the sum of 3 numbers, and we truncated all 3. So it's like it's a bit different. So let's look at that.
Might take maybe like 2 or 3 more bits, it should be okay, right?
Yeah. That's going to be the solution. Okay, so the issue here really is that it's not like this, but rather like we have 3 numbers, x, y, z. We sum them, and we get a new number, which is the sum. And then we want to compare the sum to the target. And it's like, well, it's like, imagine like you, so far, like you open 3 bits and they're equal, kind of. Okay, you didn't find the I you're looking for. Then you open the next bit, and then suddenly all 3 are 1. So then, like what you have here is like a 3, kind of, or like one with some carry. So change it. So it's not 1. The difference is not 1 because somehow you're opening 3 things at the same time and getting all the contributions. So fine. Like you ask 1, 2, 3. Like that's going to be the solution. You ask, is there a triangle? So you truncate the same way, but then you ask, is the weight equal to 1? or is there a weight that's equal to 2 or 3 or it's constant number? So let me formalize it a little bit, and then we'd be done. So lemma prime is that the sum of three numbers is greater than a target if and only if there's an I such that the sum of these things so it was like before, but instead of just equal to 1, we have 1 to 7. I said 3, it should be 3. It's just easier to prove with 7, so I'll just do that. But maybe you can prove it yourself for 3. Okay, so here's the proof. You see when I write here? First, let me say, like, once we have that lemma, then we're done. The same reduction now works, except that we ask, is there a triangle of weight 0, or 2, or 3, or 7, and that's it. And this reduction is efficient. Like, how many calls are we making? It's just log u. And u is polynomial, so it's like a log of log n overhead. So the message is you can reduce the less than, like negative or minimum, to exact with a logarithmic overhead in the size of the numbers. So here's the proof. So there's two directions. Like, first direction is easy. If like the sum of the numbers is, of course, greater than this. This is just taking the numbers, dividing them, and then taking the floor, so it can only get smaller. So if this thing was larger than 0, then of course this is larger than 0. Sorry, I wrote it with a T. So I'm always thinking about T being 0, so let me just prove it with 0. Yeah, there's no T. So I want to show that if the sum of the three numbers is positive, then there will be an I where this happens. And the first direction is easy. If this happened, the sum truncated is positive, then of course the original sum is positive. And then for the second direction, so now suppose it is positive, suppose that the sum is positive, let me show you that there will be an I for which it's going to be positive. So let I be such that the sum is between 2 to the I plus 2 and 2 to the I plus 3. Okay, so this is some positive number, so it's at least 2 to the I plus 2 for some I. And at most this for, it's just like you look at the multiples of 2 and it's somewhere there. So then, we look at this expression. So this expression is at least the same without the floors, which would be this. But then this is more than 2 to the I plus, less than 2 to the I plus 3. So this is less than 2 to the I plus 3 over 2 to the I, which is 8. and that's where the 7 is coming from. So this will be less than 8, so at most 7. And then this is at least, again, the expression without the floors, but pessimistically, each time you take the floor, you get a -1. It's -3. And then this is at least 2 to the I plus 2. And this is 1. That's the proof. Yeah, I mean, this is just some calculations, but I think the intuition is fairly clear. Any questions about this? So if not, let's go to lunch. So you have the handouts. You're welcome to start discussing over lunch and then after the break. In the afternoon at 4, I'm going to give you a lecture about a problem, a graph problem, all pairs max flow. It's going to be like a motivational success story of fine-grained complexity. So I'm excited. It's like to show you the power of fine-grained lower bounds for giving algorithms.